Our next thing to do here is to take a little bit more in-depth look at this, what we were talking about earlier with the tangent line problem and the surface area problem. This is a very rough, very approximate, crude introduction to the notions, and then we're going to get plenty of detail. The devil's in the details, and this stuff is loaded with it. So we'll take a look at the details later on. But for now, just a rough general idea of what it is we're talking about. The tangent line problem says this. Let's suppose we have a function and let's suppose we have A in the domain. It turns out there are a few other assumptions we need to make, and we'll get there when we get there. But for now, let's assume all those assumptions we require are being made, more to come later on. I have the graph of a function here. So this is y equals f of x. And I have a point, let's call it here x equals a. Now we know if we're given, so this is all we're given. The only thing we know is the equation that defines the function, and we're given a single point on the x-axis. Now from that, we can create the value f of a. So essentially, that's all the information we have. Nothing else is known. And our task is to find what's called the tangent line. Now, what do we mean by that? Well, we know what a tangent is to a circle. If I have a circle here, we need maybe a little terminology. A tangent is a line that intersects the circle in exactly one point. So that is a tangent to a circle. Now, what happens if we have a line that intersects the circle in 2 points? Remember what that's called? Some people use, very often as students say the word chord. A chord is only the portion here. This is a chord. The chord is only the part, the segment that extends from a point on the circle to another point on the circle. But the entire line is called the secant line. So this is called a secant line. If you've had Professor Bratz in class, he says secant. So this is the secant line. And a really dear friend of mine, Ms. Murray, she used to say secant. This is the secant line. And then we have the tangent line. All right? Well, that's for a circle. What do we mean? We're going to extend those concepts to the idea of a curve in general. So if I just have some curve, what do we mean by a tangent to the curve? Suppose I'm given a point here. What do we mean by a tangent? Well, I think the spirit of the idea is this red line. That's what I mean by the tangent. Now, in a circle, a tangent intersects the circle in exactly one point. That's not what happens here, because this does intersect twice. But when we're talking about a tangent, and we'll see this in more detail later, when we're talking about a tangent, we're only concerned with what happens very close here, in sort of in this neighborhood. In fact, many of you planning to go get your master's degree in mathematics, I'm sure, it turns out that's the official name for this. This is the official mathematical name. This is a neighborhood. So we're talking, in this region, it only intersects once. Outside of here, I don't care what happens, just in close. So this is what we mean by a tangent. And then by a secant, what do we mean by a secant? A secant would look something like that. And so it crosses over at a particular point. There are points on one side of the secant on one side of the curve, points on the other end of the secant on the other side of the curve. We can make that more official. But this is the idea of a secant. This is the idea of a tangent. Usually we say a secant in a circle intersects the circle in exactly 2 points, and that's what's happening here. But if I choose, suppose I choose, let's say this point, and draw this. Yes, this is a secant, even though outside this neighborhood it does intersect. So when we're talking about tangents and secants, we're only talking about what happens in this region. So enough of that. Let's talk about what we mean over here. What do we mean by the tangent to this curve at this point, well, I think it's pretty clear what we're talking about here is that within the limits of my badly drawn picture, that red line, which I hope you can see fairly well, that red line is the tangent. The tangent line problem is this. This is the tangent line problem. Find the equation of the line tangent to the curve at the point what are the coordinates of that point? We know the coordinates of that point are a comma f of a. All right, that's the statement of the tangent line problem. More details in a moment. Now, let's talk about the surface area problem. It comes in several different forms. The one I'm going to use is a very generalized form of it. It says this: the surface area problem, very roughly, and again, you can couch this in different language. It means this: given a region that encloses, given a curve that encloses a region in the plane. So we're given this curve, so all the points on that curve we know. And given a region that it encloses. The question is, what is the area? If I call this region R, what is the area of region R? Tangent line problem is find the tangent line. Surface area problem, find the surface area. That's the nature of the problems. It might not seem like very much, and another thing is it might not seem like these are related at all. These are two weird little geometry problems. Why should this give rise to this calculus that everybody's always on and on about? Well, it turns out that when you solve these problems, the tools that you use to find the solutions to these problems are very resilient tools, and they're very robust. And you can use those tools to find many, many other things. Now, I'm going to give you a rough sketch of how this problem is, how these problems are solved in a very, very general, crude approximation, and then we are going to fill in the details. If you hang around the coursework long enough, you'll fill in the details for these two problems, a problem of this nature. It won't be quite this straightforwardly stated, but a problem similar to the surface area and the problem very like the tangent line problem. So we're going to take a look at each of those. Roughly speaking, this is the idea. You choose a number not equal to 0. You have a large choice. You are a lot of numbers. Any number between negative infinity and infinity, subject to the constraints of our problem. Any number will do. All right? You're not allowed to choose 0, so choose some other one. Let's suppose we choose, let's pick a number out of the blue sky. Let's choose 3. All right? Suppose this distance is 3. So this is a plus 3, right? This is a plus 3. Now I'm going to fix my little picture up here. All right. Well, if I have that number, then what I have is another point on the line. See, what's the problem? What's the big issue about finding the equation of the tangent line? You might think, well, what's the big deal? Just find the equation of the line. Well, here is the issue. In order to find the equation of a line, I'm going to steal some space over here in just a minute. In order to find the equation of a line, what we need is the slope. We need y minus the y value is equal to slope times x minus the x value, where y0 and x0 are the coordinates of a point that lies on the line. Well, there we are. We're looking right at it. That's wonderful. So we got that. But then we need the slope. And the question is, how do you find the slope of a line? Well, the way you find the slope of a line, you've set through enough algebra classes to know that the slope of a line is rise over run. And in order to find rise over run, you need to know 2 points that lie on the line. And you cannot find another point that lies on this red line because it is a tangent line, and by definition, in this area, in this region, it only has 1 point on the line, on the curve. And so there is no other point. But you need to have another point so you can find the slope. But in order to find the slope, you need to have another point. But you don't have another point, so you can't find the slope, and you chase your tail. So here's the way around it. We choose out of the blue sky another number. I can choose x to be 3. I can choose this to be -2, in which case this would be -2, and here'd be my second point. You simply choose this number. I'm going to change my picture a little bit so it's a little bit more user-friendly here. There's my curve here. So that's my point on the curve. Now I know those coordinates are known because it's a plus 3, comma, f of a plus 3. This function would be known, a would be known. I could find those values lickety-split. And then what I can say is this. Consider this. Hope that shows up okay. That's a yellow line. Consider this yellow line. That's not a tangent, that's a secant line. But what we can say is this. The slope of the secant line we can find is rise, run. We can find the slope of the secant line, but the slope of the secant line is not the same as the slope of the tangent line, otherwise they'd be parallel. The slope of the secant line, however, is approximately equal to the slope of the tangent line. It's just a really, really bad approximation. But we can make the approximation better. Don't choose 3. Choose a number like 1.5. Suppose I choose 1.5. Now, this is not my extra point. Now this is. Now this is not my secant line. Now this is. And the slope of this second line is a little bit closer to the slope we're looking for. It's still an approximation, but it's a better approximation. And if I choose a different value, suppose I choose a point, instead of choosing 3, suppose I choose a really small number like 0.01. Then this point's very close. Now this is my point on the curve, and now this is my secant line. And now the approximation is very good. And if you want the approximation better, you choose an even smaller value. It should be clear to see that as the number we choose gets smaller and smaller and smaller, the approximation gets better and better and better. Well, the person might say, well, why don't we just forget the approximation? Choose 0. The problem is if I choose this number to be 0, now you're back to a single point and you no longer have rise and run. So it must be a different point than A. What we're going to do, we're going to call this point in our notation, we're going to call this point X. And one thing that we're requiring is that X is not allowed to equal A. Because if X is equal to A, this whole thing collapses and there is no slope. That's the tangent line problem. The procedure that we go through to make this happen. What you're seeing here, and this is what I alluded to in a previous video, what you're seeing here, this is an extremely offhand way of saying this. The second point I'm choosing, it's getting closer and closer and closer to A. It is getting, extremely offhand here, it's getting infinitely close. And we've introduced the idea of infinity. Now, the surface area problem. Here's how this works. Very roughly. Let this be A, let this be B. So we have an interval, AB. See, there is a nice formula for the area of a circle, the area of a triangle, the area of a sector, all those, the area of an ellipse. All those special figures have nice little formulas. So we think. We're going to find out it's not quite so nice and little, but we think we have those formulas for those. The question is, there is no nice little formula for this irregularly shaped region. You're a surveyor, and you need to find the surface area of this pond. So you need to have some sort of way to compute that surface area. So here's what we're going to do. Chop this up into a collection of equal, now notwithstanding my bad picture, let's suppose these are equally spaced. Let's call this distance delta x. So each one of these is delta x. Delta stands for change in the value. Delta x is the change in the x value. So this is the change. If any of you have studied economics, you've seen delta x all over the place. Right? Each of these is delta x. And above each of these, draw a vertical line. And boom, and boom, and boom. Now, my picture is terrible. We're assuming these are all equally spaced apart. And then chop each of these off into a nice, neat little rectangle. Now, what is not inside a rectangle? This is not, and this is not. We have some errors here. We have some values that are not inside the rectangles. But if I take the area of these rectangles and add those up, that is an approximation of the total area we're looking for. It's just a really bad approximation. This language should sound familiar. We can get an approximation, but the approximation is bad. How do you make the approximation better? We need to get rid of some of this error business. Well, the way to do that, let me torture my picture a little bit. The way to do that is to use more of these. The official language here is sub-intervals. Chop this up into very small pieces. Now, if their pieces are getting very small, the number of pieces is getting very large. And now we have very slender rectangles. And we chop each of these off at the top. And now the leftover bits are just this little piece and this little piece and this little piece and this little piece. Now, this is a much better approximation of the total area. How do you make the approximation better? Take more and more and more thinner and thinner and thinner rectangles, and these little leftover pieces begin to get smaller and smaller. Now the question, so what's happening is n, if we let n equal the number of little intervals, n is getting very large. If we had an infinite number of these little rectangles, there would be no leftover bits. The problem is you can't have an infinite number of them because the area of an infinitely thin rectangle is a line segment, and that area is 0. But as that value gets larger and larger and larger, the approximation gets better and better and better. How to resolve that issue is something we'll talk about later on. That's the surface area problem. The surface area problem is how do you find the area of a region, and the tangent line problem is how you find the line tangent to a curve. Notice, by the way, I've introduced the notion of infinity over here as well. If n gets larger and larger and larger, a way to think of it is as it goes out the x-axis. The unofficial way of saying that is x approaches infinity. As it gets infinitely large, then this approximation gets infinitely good. It's a very crude way of saying it. Those are the two problems. And what we're going to look at are the tools that we need to develop to make sure we handle this in the right way. This is loaded with detail. It's loaded with some algebra, so hold on to your hats. But we're going to talk about the tools we need to develop to answer these kinds of questions. And it turns out, once you have those tools, they can be used to do many, many other very interesting problems that are very useful, not just in mathematics, but also in all the sciences, in chemistry and physics and biology and physiology. These kinds of tools we're going to develop have wide scale of application. So that's the notion of the tangent line problem and the surface area problem. What we need to do is develop the tools to handle this notion of these are getting very, 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 very small, infinitely small. These are getting very, very, very thin, infinitely thin. How do you handle the notion of infinity? The problem is it doesn't work the way you think it should very often. So we need to be extremely cautious and develop some extremely powerful and rigid tools to be able to understand how to make these things work for us rather than we never can get a handle on it.